Good morning. More rotation. So chapter 10, we took a very good, thorough, complete look at rotational motion. And in chapter 11, we're going to build on that a bit. In particular, we're going to be looking at angular momentum. So that's kind of the remaining angular quantity that we want to take a look at. So let's get started. So there is a property of angular momentum for an object that's in rotation. Now, just for comparison, let's do this. So here's kind of my take on angular momentum. Linear momentum that we looked at just in chapter 9, so not so long ago. But linear momentum, we used the symbol p, which made no sense, and we said it depended on the object's mass and on their velocity. Well, what if we created an angular or a rotational momentum? What might that look like? And we just do the analogous calculation here. Now, the angular momentum depended on mass, so linear momentum depended on mass. So for angular momentum, let's replace mass with the rotational inertia, right? That's what we showed had the analogous properties of mass for rotational effects. And then for the velocity, this is linear velocity, let's replace that with angular velocity and then ask ourselves, could it be that simple? And it sort of is. It's not quite that simple, but the formula itself works. So angular momentum can be represented as the rotational inertia of an object times its rotational velocity. Now, with linear momentum we said it's a vector. It's got three components. And each of the individual components, px, py, and pz, and again, the p made no sense, and so for angular momentum we use L, which also makes no sense. So anyway, px, py, pz is determined by Vx, Vy, and Vz. These three statements get combined into one vector formula. Now, rotational inertia is more complicated. In chapter 10, we presented rotational inertia as if it's sort of one number for an object, but we did say that it depended on which axis we're looking at. So what happens with rotational inertia is that there is a rotational inertia around the x-axis, there's a rotational inertia around the y-axis, and around the z-axis for an object that has symmetry to it. So for an object that has symmetry, we have what are called principal axes of rotation. And what we saw back in chapter 10 was if those axes, for a cylinder, for example, if they lined up with the symmetry axis of the cylinder, that was one value, but if we turned it 90 degrees, it would be a different value. Well, in general, rotational inertias can be represented as a 3x3 matrix. Now, you guys don't have to do that, so just let me put that out there first of all. We're not going to look at any problems where we're looking outside of a symmetry axis. But just so you understand, and I think you probably, after chapter 10, you already have kind of a sense that, all this rotational stuff is kind of analogous, but it still seems like there's more underlying complexity, and there is. So the angular momentum can be written as a matrix multiplied by a vector. So the rotational velocity, the angular velocity is a vector, angular momentum is a vector, but there can be a more complicated relationship between the components. It's not like linear momentum where each component of momentum just depends on the corresponding component of velocity. The fact that we got a matrix here says that the angular momentum in the x direction could depend on angular velocities in the x, y, and z. All three of these could contribute to Lx, and all three of these could contribute to Ly, and so it's a little more complicated, or it's a lot more complicated, but we're not going to go there. All right, so, and then in terms of units, let's take a look and see. When we introduced linear momentum, this was kilograms meters per second. And so that was kilograms meters per second, which we said could also be written as newtons times seconds. Now, angular momentum, if we take a look at the units here, this is kilograms, kilograms meters squared, times radians per second. We drop the radians, but we have a different set of units. So angular momentum doesn't even have the same units as linear momentum. It's a fundamentally different quantity. The two are related. There is a relation between them, but you can't take a certain amount of linear momentum and turn it into angular momentum. At least not directly. It's not like energy. When we looked at rotational energy, kinetic energy, and linear or translational kinetic energy, those could just be added together. They both were measured in joules. That's not the case with angular momentum. All right, so I feel like this is a pretty good overview. Let's go back to that first photo. And so what we're looking here is this person's going to end up with an angular velocity. You know, they're rotating, and the skater, and there's going to be angular momentum along with that. Now, the reason that we introduce angular momentum, I'm going to go back to their first slide, where we say L is equal to I omega, which looks so simple, but now we realize it's more complicated. Angular momentum is a conserved quantity. So we saw that energy, overall energy, total energy of a system, is conserved. Linear momentum is conserved, and now we're finding out that this angular momentum is also conserved. So we'll see examples of it. You know, the textbook always wants us to remember that if we add up all the torques combined will tell us the rate at which the angular momentum is changing. Okay, and that's fine for now. I always feel like that's a little high level to start out with, so we'll see it show up from time to time. Now, if there's no external torques acting on a system, if we isolate a system so there are no torques acting on it, then dl dt is equal to 0, and angular momentum will remain a constant. And that means I times omega will remain a constant. And there's our first example of, if you can isolate something, the angular momentum of that object will remain fixed. This we looked at. So let's do a couple of calculations just to see what these angular momenta are going to look like. Now, there's actually two ways we can calculate angular momentum. One of those is I times omega. So we just saw that I can take the rotational inertia, multiplied by an angular velocity. That will give me the angular momentum. Another way we can look at this is to say that it's the linear momentum times a lever distance. Now, when I first look at those, I think, are those really the same formula? Are those sort of interchangeable? So as an example, let's say that we have an object with mass m, moving with velocity v. Well, it's got momentum, linear momentum, of m times v. So we can see that there's linear momentum here, but now what happens if we define an axis and we measure a lever distance? Now the lever distance is going to be set up so that it's perpendicular to the direction of velocity, or the direction of linear momentum. If I've got a lever distance that's perpendicular to the linear momentum, m times v, then I can take that lever distance times the momentum, and that will tell me the angular momentum. So that's one way to calculate angular momentum for a compact, isolated object. Now let's take the I omega approach and see if these really match up. If I take I omega for a particle or an object with mass m relative to an axis with a lever distance of r, the rotational inertia of that object would be given by mr squared. So the rotational inertia here would be mr squared. That would give us mr squared omega. And then what we can say is V would be equal to R times omega. So I can take, well, I can write down V is equal to R omega. That means omega is V over R. So let's substitute in the V over R. And now what we have is mv times R. So yeah, we can show that for an individual compact object, what the textbook calls a particle, those two formulas match. Then the argument becomes, well, what if instead of just one isolated particle, what if I have a big object, a cylinder, a sphere, something that's rotating? How could I calculate the angular momentum there? And I can calculate the angular momentum by adding together all the individual angular momenta. And so once we've demonstrated this for one object, one small object, we can say, yeah, these formulas are going to work in general. Now, all of the objects we're looking at have enough symmetry to them that I can be represented quite simply. You don't have to go back and fill in all those different components of the rotational inertia. So let's try something here. Let's say that this diagram right here represents Earth's orbital motion. So I can write down the mass of Earth. I can write down the radius of Earth's orbit. So this is the orbital radius. Here is the mass. And then I could write down a period. The period here to complete one cycle would be 1 year, 31.6 million seconds, and from that I can get a velocity. So I always like doing these velocity calculations for Earth because it's always remarkable to go, oh yeah, we are orbiting at 30,000 meters a second, which is like 67,000 miles an hour. So it's always a good reminder that we're traveling really, really fast. But since the acceleration effects are really tiny, we just don't notice it. Okay, it's a very smooth ride, not a lot of turbulence when we're aboard planet Earth. So the speed here is 30,000 meters per second. We can calculate the angular momentum by either approach. Let's use the top one. That seems easier. That seems more direct. So let's do that. Let's say that the angular momentum of Earth is mv times r. And that would take the m, the v, the r, multiply them all together. That's giving us, it's going to be a really big number, right? 2.70, 10 to the 40th kilograms meters squared per second. You go, yeah, it's a big number because the Earth's going really fast, and it's got a really large mass, and it's got a really large lever distance, and all of those combine to provide a lot of angular momentum. Now this is orbital angular momentum. What about the rotation of the Earth? Because not only is Earth orbiting, Earth is also rotating all on its own. And so here is the rotational axis. There's an omega associated with this. Now, this probably, I want to use L equals I omega. I'm going to use the other formula. Because now what I have is, I'm thinking of Earth as this object with a rotational axis. I can calculate the rotational inertia as 2/5 mr squared. The Earth's a sphere. I can put in the mass of the Earth. Now the big R here would be the radius of the Earth, not the orbit of the not the orbital distance, but the radius of the planet, which is much smaller. So here is the radius of the Earth. So that gives us a rotational inertia, 9.77, 10 to the 37 kilograms meters squared. Now I need to get an omega from this to put into my formula. I can get the omega by taking 2 pi over the period. And the period is 1 day. Now we looked earlier and saw that this 1 day works out to be, it's not quite 24 hours. One complete rotation is 23 hours and 56 minutes. When did we, I guess it was last chapter we talked about that. So 86,164 seconds, and I can calculate omega from that formula. This works out to be 7.29, 10 to the minus 5 radians per second. So how much angular momentum do we have due to Earth's rotational motion? And I omega gives us 7.12 10 to the 33 kilograms meters squared per second. So how does that compare with the orbital amount? And if we look back, oh, the orbital amount is like, a million times? 3 million times? Yeah, something like 3 million times more angular momentum in Earth's orbital motion compared with its rotational motion. So it's not even close. The orbital motion is much larger. Now another question we could ask is, since angular momentum is a vector, these rotations we're talking about, they're not necessarily around the same axis. So what we could do is we could define an orbital, for the orbital motion, we could define an angular momentum vector and say that is perpendicular to the plane of Earth's orbit. But the rotation is tipped. So the rotation would have to be at an angle, and then we could do vector addition. So it's kind of interesting that you can have one thing spinning in one direction and something else spinning along a different axis, and you can actually combine components, the same as you would for any other vector. So these rotational vectors work the same way in terms of vector addition. All right. So those are a couple of, I hope, familiar angular momenta. Now, what about this example that maybe you've heard about, where you have someone that's, someone's rotating. So let's say somebody's rotating like this. So they got a rotation going on, and then the person brings in their arms. What does that do? You go, well, if we have a skater, and the skater's spinning around and they have their arms out like this, when they bring their arms in, the rotational inertia goes way down. I mean, you guys can try this. I mean, you can stand up and just think, how much resistance is there when I try and accelerate back and forth rotationally with my arms out? And then how does that change when I bring my arms in? You go, wow, that's a big difference. This requires, this is a real workout. This is really easy. So you can feel the difference when you redistribute the mass so that it's farther away from a rotational axis. So what angular momentum says then is that since angular momentum is conserved, if the person brings their arms in, then I becomes really small, and that means omega will go up. So it's crazy. I mean, maybe you've seen this example with, skaters, Olympic skaters or whatever. When they bring their arms in, they start spinning really fast. And it's an angular momentum effect. It's conserving angular momentum. Let's look at a couple of examples with this. So they call this a clutch, but let's just think of it as a couple of rotating platforms. So what happens is we've got one platform rotating at an angular velocity, omega 1, and it's got a certain mass. A second platform drops down onto the first one. Now what's going to happen is, the two surfaces are going to kind of slide past each other for a while. But eventually what we'll have is both of these platforms will be moving together. Now what they're saying in the problem, they're calling this a simple clutch. Two cylindrical plates that can be pressed together or dropped so that they're in contact. It says both plates have the same mass. Mass of plate 1 is 6 kilograms. The mass of plate 2 is 9 kilograms. They both have the same radius of 60 centimeters. Initially they're separated, and the lower one is initially accelerated to a speed of 7.2 radians per second in just 2 seconds. So calculate the angular momentum, calculate the torque required to accelerate that plate and then have the plate that's at rest, plate B or plate 2, drop and come into contact. So let's take a look and see what happens with all of this. So there's a lot going on here. First of all, I'm going to take that first plate, because that's the one they're asking about at first, and say that it has an angular velocity. Well, we're going to, excuse me. So we're going to say that there's a torque required to create an acceleration. So I'm going to need some kind of a torque to create the acceleration. Now it's a cylinder, we're treating it as a cylinder, so we can say the rotational inertia is 1/2 mr squared. I can put numbers into that, and the rotational inertia works out to be 1.08 kilograms meters squared. So that's how much rotational inertia we have in the cylinder. Now it also says that we're able to accelerate this from rest to 7.2 radians per second, and that all happens in 2 seconds. So that would give us an acceleration of 3.60 radians per second squared. So I've got the numbers I need. I know what the rotational inertia is. I understand, I've been able to calculate the rotational acceleration that it has. And so I can multiply those numbers together and say, here's the torque. We are using 3.89 Newton meters of torque to bring this first cylinder up to speed. Now in part B, we're going to come back and say, how much angular momentum does that represent? So the angular momentum can be calculated as I times omega, and here is that rotational inertia that we calculated, and here is the speed that we brought the cylinder to. So if I multiply I omega for the angular momentum, I get 7.78 kilograms meters squared per second. Now, had a friend from whenever I hear the angular momentum is equal to I omega, I always remember I had a friend from kind of way back, really, almost from elementary school, actually from elementary school, and he had gone off to college and I went to a different school. Anyway, he ended up going into mechanical engineering and working for a company, I guess mechanical / electrical engineering. He was working for a company called I omega, and they made external drives back when computer storage involved some kind of a drive that was spinning. And I thought that was such a clever name for a company that made external drives. They called it I omega. And I thought, I always wondered, I thought, I omega, what does that mean? And then one day it hit me. I thought, oh yeah, I omega. I omega is angular momentum. It's something that's spinning. Anyway, so we've been able to calculate the torque that we needed. The torque tells us the rate at which the angular momentum is increasing. And then we've also been able to calculate how much angular momentum we have in that object. Now we're ready. This object, this lower object is moving. This other one's going to be dropped onto it. So here are the two rotational inertias. So what we can say is, before this one drops, the angular momentum we have in our system. So those two objects now represent a system, and there's nothing coming in from outside to affect them. They're isolated. And that means that when M2 and M1, when M2 comes into contact, that angular momentum will end up being shared between the two. We can kind of think of this as an inelastic collision. It's an angular momentum collision. And so before the collision, the angular momentum we have is I1 omega 1, but afterwards, they're both going to be rotating together at the same angular velocity. That would be I1 plus I2 times omega t. Now, the angular momentum before and after, those are going to be equal because we've isolated these two objects, and angular momentum should be conserved within that system. So that would say that the angular momentum after equals the angular momentum before. It says that the rotational velocity after is equal to the rotational velocity before times I1 over I1 plus I2. So these are the expressions for I1 and I2. We can write those out following the formula we have here. Well, all the r's cancel out because the r's were the same, at least in this example. The r's were the same, so we can do some canceling. The r's go away, the shape factors cancel out. What we're left with is the angular velocity after is equal to this factor times the angular momentum before. Now it's a ratio of masses, that's 6 kilograms compared with 15. So it used to be all the angular momentum was in the 6 kilogram object, but now it's being shared between the 6 and the 9 kilogram object, and this is what the math is telling us. So that's saying that the angular velocity will drop to 40%, 0.40 of what it was before, and we can go in and calculate what that number is. All right. So again, it's analogous. This example works the same way that collisions with linear momentum worked. Okay. Ooh, here's another example of angular momentum conservation from astrophysics. And this is the formation of a neutron star. So astronomers at one point identified stars that they could tell were rotating very fast because of the way that a particular signal, a very regular signal, was being transmitted. And they realized it was very regular because every time the star rotated, the signal would repeat. At first they thought this might be signs of extraterrestrial life, so kind of interesting when neutron stars, or pulsars is what they're called, pulsars were first discovered. They thought it was such a regular signal, they thought how could that be generated naturally? And then people realized, astronomers came to realize, these were what we refer to as a neutron star. Neutron stars form from the cores of large stars that have collapsed. And the key feature for us here is that at the end of when a star runs out of fuel for the nuclear fusion reactions, then gravity collapses the star. There's nothing pushing back from the core, and so gravity ends up collapsing the star, and the collapses can be quite extreme, quite dramatic. So they're saying that let's imagine we have a star with 2 times the mass of the sun, with but it's the size of the sun, and it has a frequency of 1 revolution every 100 days. So this is the star, and then it collapses to a neutron star. These neutron stars are only, the radius they have here is 10 kilometers. So you figure a diameter of 20 kilometers. That's a tiny object. Imagine something the size of the sun collapsing down to something the size of Oakland, right? Something like that. And so it's this enormously large object, this star, collapsing down to this tiny, tiny remnant that's referred to as a neutron star. Now, as far as the name, what happens in the formation of a neutron star is this. When gravity starts collapsing everything together, the electrons that remain in that star are kind of big and bulky. They end up taking up a lot of space, and that prevents further collapse. But there is a particle physics reaction where electrons can be converted to what we call neutrinos, and neutrinos just fly off. So the neutrinos will fly out of this reaction. They won't be held together by the star. When electrons turn into neutrinos, at the same time protons turn into neutrons. This is a W. It's a particle that makes up the weak force. We'll see this in Physics 3b, very last chapter of, or very near the very last chapter of the course. So you eliminate the protons that are the electrons that are big and bulky, and in the same time the protons turn into neutrons. And what that does is it leaves this star to be made primarily just out of neutrons. So the star becomes kind of a neutron star. It's the neutrons are what are left. Anyway, that's the reaction that happens when you get these extreme gravitational collapses, and then the protons turn into neutrons, the electrons turn into neutrinos. Let's see, so here's this star. Now it has a period of 100 days. I think the sun has a period of, what, 20, 25 days, something like that. And it's not a rigid object, so different parts of the sun are actually rotating at different rates. But something like that. So this star, not so different. On average, the star's material completes a rotation every 100 days. Now the angular momentum before and after the collapse are going to be the same. So what we can do is take 2/5 mr squared times 2 pi over the period, so that would be omega, and 2/5 m r2 squared, 2 pi over t squared. So I'm going to try and do this just setting up the formulas and then canceling out as much stuff. It's kind of like doing a ratio. What we're finding, in fact it is a ratio, the 2 pi's will cancel out, the masses will cancel out, the 2/5 will cancel out. So during the collapse, we expect that most of the mass remains with the star. And when we solve for the ratios, what we get is period 2 divided by period 1 is going to equal R2 divided by R1 squared. So that's what's left from that. We started with angular momentum conservation, wrote in mathematical expressions for the rotational inertia and for the angular momentum, and that's what we're down to. Now, what we're saying here is that the radius initially was 700,000 kilometers and it dropped to 10 kilometers. We square that number, and it turns out that the period of rotation becomes 2 times 10 to the minus 10. That's what the ratio is. So the initial period was 100 days. When we multiply by that factor, we actually get a period now of 1.76 milliseconds. So a couple of thousandths of a second is the time required for that star to rotate. Now, I took the inverse of that number to get the frequency of rotation, and what it says is it's rotating 567 times a second. All right, so pretty fast rotation rates. Over time, the rotation slows down. Some of this angular momentum is radiated away, actually. And so, yeah, it's kind of remarkable that you run the numbers and you think, oh my gosh, if a neutron star really forms, it's going to be rotating at a really high speed. Is there anything out there that we can see that behaves that way? And it turns out we do. Observationally, we see these stars that are rotating at these really, really high frequencies. All right, here's another example. Here is somebody walking along this platform, and they should build these in parks, right? They should have a big platform. I mean, I know they have the merry-go-rounds, right? And those are kind of fun to go and play around on. But a really big platform like this, where people could get on and play around with angular momentum. So here's a big platform. I guess it's a cylinder, we'll see. Now, what happens is the person starts walking in one direction. Well, that creates an angular momentum in that direction. If the system is isolated, if this platform is sitting on an axis and it's got bearings and it's well lubricated, then the platform is going to end up spinning in the opposite direction. So right now, with the person going in this direction, we can think in terms of that right-hand rule. If the angular momentum is here, then if the person is going in the direction of my fingers, then the angular momentum would be here. The platform's going to respond, though, in the opposite direction. So those two angular momentum vectors cancel out and become zero. If you remember, before the person got on the platform, there was no angular momentum, and there continues to be no net angular momentum. So if the person goes one way, the platform's going to rotate back in the other direction. All right, now let's have this person run on this circular platform. So it's the same picture we saw before. The person is 60 kilograms. They're at the edge of a 6-meter diameter circular platform. So it's big. 6 meters is going to fill the room. Mounted on, there you go, frictionless bearings, and it has a moment of inertia, or a rotational inertia, of 1,800 kilograms meters squared. So everything is initially at rest, and then the person begins running at a speed of 4.2 meters per second with respect to the Earth. So this is an outside observer, not somebody on the platform, but somebody outside measures the person going at a certain speed in one direction. The platform is rotating in the opposite direction. How fast will that platform be rotating? Well, here we go. So we've got these two objects. We've got the platform and the person. And what we're saying is whatever angular momentum a person has because of running in this direction, that has to be equal in magnitude and opposite in direction to the platform rotating back in the other direction. So this person runs this way, the platform responds. They're exerting torques on each other. The angular momentum for the person, I feel like most easily we can use mvr. The rotational inertia for the platform, or the angular momentum, can be written as I omega. So there's an example of using the two formulas that we have kind of set out there for angular momentum, and just pick out whichever one is easier to work from. So again, the mass of the person, the little m, is 60 kilograms. The radius of this platform is 3 meters, and the rotational inertia is 1,800 kilograms times meters squared. Now I'm guessing it's a cylinder. I wrote down 1/2 mr squared. I don't think that ever comes up. So anyway, let's take this formula, solve for angular velocity. Now mvr, that's the angular momentum of the person. That's 60 kilograms moving at 4.2 meters per second at a distance of 3 meters from an axis that we are considering. And that all gets divided by the angular, or the rotational inertia, 1,800 kilograms meters squared. That works out to be a speed of 0.42 radians per second. Okay, and so so I took the radians per second and I converted that. One revolution is 2 pi radians. That works out to be 0.066 radians per second. And then I inverted that to get a period. So the platform is going to turn once every 15 seconds. Okay. Now the person, how fast was the person going? 4.2. Let's see, what would the circumference of this be? It has a radius of 3, so I need to multiply that by 2 pi. 6, 18. Now the circumference is going to be somewhere around 20 meters. So it's going to take this person 5 seconds maybe. So it's going to take this person maybe 5 seconds. I should have run the numbers. I didn't do that. But now I'm thinking that's kind of an interesting question here. The person is going to take about 5 seconds to complete one rotation, at least if I'm thinking about this correctly. Yeah, let's say that. So it's going to be about 5 seconds for the person. The platform, meanwhile, is taking 15 seconds to rotate once. So the person's going to go around 3 times for every time the platform goes around once, but bottom line is it's the angular momentum that's being conserved here. Oh, I did go in and use this. Let's see. So I went in and estimated what the mass of the platform would be. That's useful for comparison. So using the formula for a cylinder, I plugged in the values for the rotational inertia divided by r squared, and I got 400 kilograms. So that's kind of useful to think about. The person was 60 kilograms. The platform is 400 kilograms. The person's mass is all concentrated right at the edge. the platform's mass is kind of spread through the middle. All right, so that's the effect on this. Okay, let's move on and take a look at another example here. So here is this bicycle wheel, and what we're saying is, ooh, it's your physics teacher. There you go, physics teachers demonstrating angular momentum. So here's the bicycle wheel, and it's going in this direction. It's got an angular momentum vector in pointing upwards. What happens if the teacher now flips the bicycle wheel over? What's going to happen? And things are going to start moving, because initially, let's just make up some numbers. Let's say that there's 5 units of angular momentum with the bicycle wheel flipped this way. But when we flip it the opposite direction, now it's -5 in the coordinate system that we've set up. So flipping the wheel over changes the angular momentum. Well, I've got to conserve that amount of angular momentum, and that says that the platform then will begin moving in the original direction of the bicycle wheel, and it will have 10 units of angular momentum. So by flipping the wheel over from +5 to -5 angular momentum units, that's a difference of 10, and that transfer of angular momentum will show up in the platform. So the bicycle wheel's angular momentum changed by 10, the platform will acquire that motion. Ooh, we are going to introduce what we call the vector cross product. So we looked at a bunch of examples with angular momentum and how it's conserved, and we'll get back to some more examples, but right now we need to take a look at a different topic, and that involves using vectors to calculate torque. So this is kind of interesting too. Up until now we've been using a lever distance, and we said that the lever always had to be perpendicular to the force. Well, using this new notation, we'll have a different way of representing how that works. So this is referred to as a vector cross product, and kind of the best example to work from is to say we've got 2 vectors now, and they're not necessarily perpendicular. So I've got a lever vector, and I have a force vector, and when I carry out this operation of cross product, I get the torque vector. Now, what does a cross product mean? And cross product means this. So let's take a look at this object, and kind of like the picture before. Let's say that we have a lever distance that is defined to be the vector that takes us from the point of rotation out to where the force is being applied. So again, I've got a lever vector, R, and then I've got a force vector off at some direction. Now, when we carry out the cross product, what that's keeping track of for us is that the lever could be divided up into components. I can take that lever and divide it up into X and Y components. So let's think of it that way. And then the force also could be divided up into force components. So I've got X and Y as lever components, and Fx and Fy as force components. Now if I look at that and I use my reasoning and what I learned in chapter 10, what I see is that the torque is equal to lever distance X times force Y. It's the lever distance X that gets multiplied by the Y component of the force. And then similarly, it's the Y component, similarly, the Y component that is the lever distance for Fx. So we could say that the torque then, the torque from that diagram, would be X times Fy minus Y times Fx. And this is what a vector cross product does. It picks up different components. So the X doesn't line up with, the X components don't get multiplied together. Instead, opposite components get multiplied together. Now there's a minus sign here. If you take a look at the diagram, the way it's set up, the x times Fy is in the positive direction, the torque that's creating, whereas the y times Fx is in the negative direction. So there's a minus sign between those components. Now, if we this is just for the xy plane. If we generalize this, what we could do is, first of all, take what we've got here, the x Fy minus y Fx. We could call that torques around the z-axis. What those torques are doing is they're tending to rotate the object so that there will be an acceleration, a rotational acceleration around the z-axis. And then we could generalize it to 3 dimensions, and we could calculate how much torque would be in the x and the y and the z, just following these the pattern of x, y, z. So we can alternate the x, y's, and z's through the formulas, and that's what we come up with. Now, that's a little complicated. It's a little intimidating, maybe. What it means is I've just got to pay close attention to components of my lever distances and components of my force. But what this will allow us to do is to systematically go through and calculate how much torque we have in each of the possible components. So when we combine all those individual components of torque into an overall vector torque, that will tell us the direction that the torque is oriented in once I've calculated all the components and combined them. Now, the other feature of vector cross products is you go, well, how much torque does that give me then if I carry all of this out? Well, we can show, and we're not showing the details here, but the amount of torque that we get is equal to the magnitude of the lever distance, magnitude of the force, times the sine of the angle between those two vectors. So this is going to give us the same answer that we saw back in chapter 10. But it generalizes the calculations so that we can work directly in terms of components. So we don't have to make sure that the lever distance and the force, they don't have to be perpendicular now. We can treat them as vectors, and carrying out the vector product will make sure that perpendicular components are being combined. All right, so in general, torque, it turns out, is not at all the only physical quantity that depends on a cross product. It turns out that all the rotational vectors can be written as cross products in different types of formulas. Torque just, to me, feels like the most intuitive of those. So in general, what we can do is we can take any two vectors and follow those rules that we set out for the vector cross product. Now, if I take the magnitude, and we said this earlier, then it's the magnitude of A, magnitude of B times the sine. The direction of the cross product is going to be perpendicular to the plane defined by the vectors A and B. So once I have two vectors set up, and we could go back and look at this. Once we have two vectors set up, here is the R vector, here is the F vector. They define a plane. In this case, they define the XY plane. There's only one plane that contains both of those vectors. Now, the cross product will be in a perpendicular direction. And the way that works, the way we figure the direction, is we can take, now this is written as A cross B. And so the first vector, now there's different approaches for these right-hand rules to keep track of directions. So we have what are called right-hand rules, but they vary. The one that I prefer the most is not the one in the textbook. I like the one where my thumb is vector A and my fingers are vector B. And so if this is vector A and this is vector B, the cross product points away from my palm. Okay, so vector A, vector B, and the cross product points outwards from that. If we go back and look at the torque diagram that we just took a look at, what that would tell us is, let's see, my thumb is in the direction of vector R, my fingers are in the direction of F, and if I do that, then the torque is pointing out of the board in the Z direction. So that's why the torque in the Z direction depends on components of F and R in the X and Y. Okay. It's a bit tricky. So make sure you practice looking at these right-hand rules. Now there's another way that you can set up, this is the formula here. So the formula for the torque formula, A cross B, is equal to all of this stuff going on here in terms of directions I, J, and K. If you've seen this in math, and maybe you have or haven't, in mathematics they define something called the determinant of a pattern of numbers. So you can write this in determinant form as a way to remember. I just write it out, you know, the way that we wrote it before. So determinants will work, but you can't just write it like this. So I know it's a lot to write, but it doesn't take up that much more space than the determinant. And that's just it. That's what the pattern is. You would think, isn't there an easier, simpler way to represent it? And no, that is the cross product written out in terms of components. Okay, now there's some interesting properties with cross products. If I take the vector and cross it with itself, that gives me 0. Because the components are going to be, you know, the components won't be perpendicular to other components. If the vector lines up with itself, there's no perpendicularity between those two vectors. So the cross product actually is 0 for two vectors pointing in the same direction. Cross products are largest when there's a 90-degree angle between the two vectors. 90 degrees, and that's how torque behaves, right? Torque behaves maximally if the two vectors are at 90 degrees. Now this is an interesting property, is A cross B is equal to minus B cross A. If I go back in and I just reverse the order of the two vectors, I end up with a minus sign. So this property it's not commutative if I reverse the order of the cross products. And then there's a distribution of the cross products, which we're not so interested in. There's also taking a derivative that follows the product rule for taking derivatives. In any case, it comes down to coming up with some kind of a right-hand rule that you can use to keep track of vector directions. Okay, now what we can do then is we can go in and define, see how we're doing with time here, got just a few minutes maybe. The torque can be defined around a point. So up until now, we've been thinking of a torque as being measured relative to an axis. But now we can actually show that, or work in a bit of a different mode, where we're really thinking in terms of a point. So there is a point located right there, and I can take a force that's acting on some object located at this point. So for a particle, the torque can be defined around a point. So here is the origin of the coordinate system. So it's not an axis anymore, it's a point. There is the object, there's a force acting on it, and the torque can be calculated as R cross F. Okay, so we'll see what that means for you guys in terms of actual problem solving. That might be a good point to take a break. So I'm going to go ahead and stop there. We'll take a break, and then we'll pick up after. If there's any questions, let me know.